Hello everybody, my name is Francesco Rossetto and today I will talk about how AI/ML can improve a fundamental part of a cellular system, CSI reporting. Before going into the live part, let us provide a few important background details. In the CSI report compression setting, a UE transmits a compressed CSI report to a base station. When AI/ML compression comes into play, both the UE and the base station include a beamformer, compressor and decompressor respectively. We at Rohde and Schwarz want to early investigate this exciting feature where AI is deployed also at the base station side. In this sense, two aspects are needed. On the one hand, our base station emulator, the CMX500, must be able to run in real time a neural network, and on the other hand, a UE capable of CSI compression is required. Since this feature is not yet officially standardized in 5G and no commercial UE supports it, our R&D labs have replaced the UE side with an appropriate UE MOX that can support the AI/ML CSI compression. In a first approach, our R&D labs have used a software-defined non-real-time UE named MATLAB UE. In this setting, the UE is configured with a valid S1 configuration for CSI reporting and replaces the conventional CSI bits with those generated from the neural encoder. We remark that this approach tries to be minimally invasive of the 5G standard, since the existing format of CSI transmission is not changed. For instance, the CSI bits are transmitted on the uplink as expected in a conventional CSI report. Just the length and the interpretation of the CSI bit string is different than usual. We have implemented this approach in the CMX500 and in our in-house software-defined UE, and recorded a video with an execution of this scenario. Let us go through it. You can see a representation of the setup with the CMX500 connected to the MATLAB UE. Let us remark that the CMX500 has been extended so as to be able to load a user-defined neural network decompressor. We will first spend a few words on the used neural network architecture, which is in IM-CSI-NET. This network is based on dense layers, whose inputs are the subband beamformers stacked on top of each other. This concatenation generates a single numerical vector passed as input to the network. The output of the encoder is then quantized by a scalar quantizer into a bit string, which is then transmitted by the MATLAB UE. The CMX recovers the CSI bits and passes them into the neural decoder and reconstructs the beamformer. The top right tile on the screen shows a comparison of the reconstruction quality between the neural network, the blue line, and the 3GPP E-type 2 baseline, green crosses. As you can see, the AI-based compression can significantly reduce the number of necessary CSI bits for the same reconstruction quality compared to the state-of-the-art CSI reporting from 3GPP. You may wonder which scenario we are discussing. We simulate a random drop of the UE in an urban environment and generate the fading channel correspondingly. As time progresses, the MATLAB UE computes new reports and the CMX500 decompresses them. In this environment, we can replay the same set of channels, and therefore we can compute the reconstruction accuracy for both the neural network-based compression and the 3GPP E-type 2 baseline. The AI-based approach is mostly superior to the 3GPP baseline in spite of the much smaller reporter size. An alternative to test this AI signal processing is to replace the UE with a 5G signal generator, the Rohde and Schwarz SMW200. The SMW200 can generate 5G uplink signals And in this setting, the SMW200 sends a modified uplink signaling packet on push. More specifically, the SMW200 generates a so-called uplink MEC-CE. By other words, an uplink signaling packet at MEC level. And the special thing about this packet is that it includes the compressed CSI report as well as much debugging information. This approach is not really spec compliant, since no CSI report is normally transmitted on an uplink MEC-CE, but the additional information greatly helps to debug this feature. The CMX500 continues to work as a base station emulator and processes the uplink packets. Let us have a look at the devices and at the demo. The CMX500 can be controlled by means of a Python-based scripting language called XLAPI. And here is a very simple example scenario. Let us stress that in this scenario, we can name a neural network decoder that will be uploaded to our device. You can also see in this script that the file with the MEC-CEs for the signal generator can be defined. So effectively, both sides are now tuned for execution. We mentioned that we want to transmit a user-defined, non-spec compliant set of MEC-CEs, and this set of MEC-CEs can be set in the Python-based scenario. Let us have a quick look at this file in the SMW200. In order to do so, we open up the 5G configuration, go to scheduling, select the subframe where we want to transmit the uplink MEC-CE, and then go into the user settings. Under properties, then we can name a text file which includes the user-defined payload. We then go to the CMX500, our base station emulator. For the sake of brevity, we show a message log at the end of the scenario. Let us then open such a file and show the two key messages from a log. First, let us have a look at the SE1 configuration. You can notice the CSI reporting. Right at the end, we see that we can name a neural network that can be configured in the CMX500. Moreover, we mentioned that the CMX500 is able to receive the UE uplink, decompress the information from the UE, and display it for further evaluation. Indeed, in this message, you can see both the output of the neural decoder and the computed beamformers for the downlink. That was all from my side for today. I hope we could show the ability of the Rohde and Schwarz devices in early testing of AI algorithms for FreeHPP.